All right, so last time we started section 13.7 where we're going to find extrema of functions of several variables. And we defined some things that you already knew, basically local max, local min, local extrema. We talked about critical points being places where the partial derivatives are zero, or we have this does not exist sort of a feature going on, and we talked about how, yes, that's true, but usually the part A is the one that we end up having happen more often than not. And we talked about the fact that if we do have local extrema, they have to be critical points as well. So we can actually find critical points as testing points for that. We defined what a saddle point was last time, and a saddle point, we had this image of a horse saddle. We also talked about how that works in terms of the partial derivatives. The partial derivatives are basically going to be a maximum in one direction and a minimum in another direction is how it ends up working out. And then we had this wonderful second derivative test and has lots of great features that are very, very useful for calculation of maximums and minimums. And we're ready for an example. Does that sound good? In a nutshell, what we did? Yeah? Okay. So we're going to start with an example. We are going to locate and classify all critical points and I'll put this in here. It says it in your book, but it's using theorem 7.2, the second derivative test. That's how we're going to do this. We're going to start with a function, f of x, y, equals the cosine squared of x plus y squared. So jot that down, and then we'll go back and look at the specifics of that theorem that we sort of glossed over just a moment ago to see what the steps are we need to do. Okay, so this was the second derivative test. The second derivative test tells us that we are going to find second partial derivatives, right? We're going to find f sub xx, f sub yy, and then f sub xy. We're going to do a determinant between those values. And we're going to find out that that gives us a point. Sorry, that doesn't give us the point. We're going to use that at the testing point AB. So the AB are the critical points from back up here. The critical points are finding the first partials and setting them equal to 0. So we're going to find, and it doesn't matter what order necessarily you do these things in, but you're going to find first partials, you're going to find second partials, okay? So, and at some point you're going to find where the first partial is equal to 0. So, let's take a look at this function right here. And you guys are fantastic at first partials, so somebody tell me what is the first partial derivative with respect to x? Negative 2 sine of x. I think we might be missing something.
I forgot to train.
James is right. Can you help him, James?
I need a cosine of x.
We do. Okay, so it is actually a chain rule, and so we have the negative 2, right? So we've got the 2, and then cosine of x, and then we're going to get the negative, and then the sine of x. So we actually have this. So we're treating, just in case I glossed over that, we're treating that like this, right? There's a chain here. We brought the 2 down, we rewrote, and we took the derivative to the inside. All right, so let's do the first partial with respect to y now. You like that one? 2y, yes, that's right. I think Jordan got the easier one. All right, so what we need is we need to know where these are equal to 0. Agreed? Because that's going to be critical points that we need to test. Well, we need to set each of them equal to 0. And we'll solve the second one first because it's easy. When does the second one equal 0?
0.
Yeah, y equal to 0. So y has to be 0 for this to work, okay? So the only value that y can be is 0. How about the first values, though? What about that negative 2 cosine x sine x equals 0 business?
Well, we have 9%. 0, 0.
Right. We basically need to know where sine of x is equal to 0 and cosine of x is equal to 0. Okay, so for sine, this happens at 0 and pi, excuse me, and, sorry, 2 pi, and so forth. And for cosine, this happens at pi over 2, 3 pi over 2. Yeah, and so forth, right? So we actually have lots of points that we could be testing to see if they are maximums and minimums. Now, some of them are going to give us the same results. Now, it sort of makes sense that we would have lots of maximums and minimums on this graph, doesn't it? I mean, it's got a sine or cosine squared in it. So the idea of it sort of bouncing up and down makes some sense to us that there would be several places where we have local maximums and local minimum values. So in other words, we actually have several points to test. And I don't think they told us specifically what to test on this one. So we're going to have to take a look at something like 0, 0. If x is 0 and y is 0. Y is always 0 in this function, right? Because we know that the y has to be 0 from the first partial with respect to y. And then the x value, so something like pi 0. And we're going to have 2 pi 0, and so forth. And then we're also going to have the pi halves 0. And 3 pi halves 0. And 5 pi halves 0. And so forth. So there's lots of possible values where we could have maxes and mins. But our expectation is probably the idea that most of these are going to give us the same result. We're probably going to get the same value out of all of them. So a bunch of maximums, and the maximums are all going to be at, say, the pi values or at the pi half values or something like that. That's sort of our expectation. So we'll see if that expectation holds as we move forward. The next thing that we're supposed to do then is we're supposed to take the second partials. Okay? So I need the second partial with respect to x, the second partial with respect to y, and then I need the mixed partial. So f sub xx is what? It is a product rule, right?
So you do, I guess, the sine first. Related to cosine x, cosine squared.
Okay, so you have -2 cosine squared x. Is that what you told me? Okay, and then what?
And then plus 2 sine squared x.
Right. Everybody good with that? All right, so since I've already got fx written, let's find, you know what? We'll find f sub y next. We were given f sub y was 2y, right? Is that what I had? So we need f sub y. That one's 2. That's very nice, isn't it? And then we need f sub xy. And remember f sub xy, when things are smooth and continuous, and these are because these are polynomials and trig functions, like sine and cosine functions, this is equal to f sub yx. So if you really want to take the partial derivative of -2 cosine x sine x with respect to y, you can do that. Or what could you do? Yeah, I could take the partial derivative of 2i with respect to x, which would be easier. Agreed? Because the partial derivative of 2i with respect to x is 0. What's that?
The other one would be 2. Because it doesn't have any y, isn't it?
But you still have to end up doing a chain rule to get to that point. That's my only point, is that I'd have to do the chain rule if I do the first way. If I do the second way, I can just see it very straightforward. But I get 0 either way. It doesn't make any difference.
Isn't that just a number, though, with respect to
You
y?
know, she's saying to get to f sub x, you have to do the chain rule. But you could just do f
Oh,
sub
you mean
y.
this one right here? Isn't it? That you're right. That's true. I didn't think about that. You're right. Because there aren't any y's in it. That's true. Excellent. So it works the same way both ways. We've got a partial derivative that's 0. So we're actually ready to do the determinant. Okay. You can write it in a matrix form if you like. You don't need to do that. But the determinant is f sub xx, f sub yy, minus f sub xy squared. So this is the -2 cosine squared of x plus 2 sine squared of x times 2. That's f sub yy. And then minus 0 squared. So this gives me a determinant value that looks a lot like the original one I had. It just I'm going to distribute the 2 through. So I've got negative 4 cosine squared x plus 4 sine squared y. Okay, are we all good with that? Okay. Now, the nice thing you notice is this actually has only the variable x in it. That's going to be friendly in a moment because we're about to evaluate some things. Although it's not really all that friendly because our y value is 0 anyway that we're evaluating at. But we are going to evaluate this determinant value at our critical points. So we'll start with the d of 0, 0. That was the first critical point we listed right here. So we'll just start with that one. So on that one, if I plugged in x is 0 everywhere, what do I get? Negative 4, right? Because I have negative 4 times cosine squared of 0, which is 1, and then the sine squared goes away. So this is negative 4. But notice, this happens not just at 0, 0. Where else is this going to happen? This happens at pi 0, and it happens at 2 pi 0, right? And so forth. So we don't need to sort of retest all of these points. They're all negative 4. Because when I plug in pi or 2 pi, I end up getting a cosine value of 1. It squares things, or negative 1, which is still squared. This gives me a positive value, and the side squares go away. Nathan, you're looking confused. Did I lose you? It would, but then we're going to square it. Yeah, so that takes care of it. But that's a good point to notice is that it does oscillate in terms of the signs if we didn't have it squared. Yeah. All right, and then the other one that we have are the half pi values, right? So like pi over 2, 0. And if I get pi over 2 and plug in pi over 2 for x, what do I get? I actually get positive 4 because I'm actually going to get a value out of the sine squared now, correct? And this is the same value that I get at all those other half pi values, right? 3 pi halves and 5 pi halves and so forth. So looking at those, we actually need to make a decision now based on the determinant information that we were given before. So let me scoot this down just a little bit so we can go back and actually decide that. All right, take a look over here. Oh wait, I'm on the right side, this one. The very first part tells us if the determinant value is greater than 0, we're in either case 1 or case 2. We've got local extrema. Okay, so that's the second one that I actually did, right? All the pi half values, I had positive value down here. This is all values that are greater than 0. So I've got some local extrema happening here, either local maxes or local mins or something. I mean, I don't know exactly yet, but one or the other. And the way that I decide which one it is I take a look at the second partial with respect to x value. So the second partial with respect to x is up here. And if I plug in x equals pi halves or 3 pi halves or 5 pi halves into there, the question I need to have answered is it positive or is it negative? So when I take f sub x and I evaluate it at pi halves 0 or 3 pi halves or 5 pi halves, all of those, what do I get? I get a positive 2. I do. So this is positive 2. It's greater than 0. So if it's greater than 0, it opens up, right? And if it's opening up, it's a local minimum. So this tells me I have a local minimum at all of those values. Lots of them. I'll write it all out cleanly in a moment. But let's go back and do the other one as well. So on the other one, I found that this one's determinant value was negative 4. What does that tell me? It's a saddle point, and that's actually very helpful because there's nothing else to test, right? So this is a saddle point. I've got lots of saddle points. All right, so let's write out kind of what we have here. So our local minimum values are at. How can I write this so that I don't do a comma dot dot dot? Do you remember from trig? N pi. And then it's 0, right? What is n, Caleb? Yes, where n is an integer. We worked with that a little bit in Calc 3, that kind of notation too. And then the other one is that I have saddle points are at, oh, I'm sorry, that was the n pi one. I'm going out of order. The saddle points were the n pi ones. How do I get my half pies?
Pi over 2, so it'd be n pi over 2 or
We can do that. It's a little awkward. We usually still let n be an integer. Do you remember how we do it?
n over 2 plus 1.
You're close. We do n, 2n plus 1 over 2 pi. 2n plus 1. So if I had 2n, that would give me all the even numbers, right? So 2n plus 1 gives me odd numbers. Sometimes you see k's. We used k's in Calc 3, right? A lot of k's when we were talking about things like this where we're letting things sort of iterate. And then our saddle points were at the n pi, or n pi zeros. Again, where n is an integer. Okay, any questions on that one? That one was very friendly because we had a lot of things happen over and over again that were identical, right? Because of the trig function involved in it. So let's take a look then at another one. This one is same directions. Not going to have trig in it. This is fxy, f of xy, 2x squared plus y cubed minus x squared y minus 3y. Okay, so lead me down the road. What are we doing first? Find f sub x. Okay, so someone who hasn't told me one today, tell me what f sub x is.
4x plus 2xy.
Thank you, Nathan. Does everybody agree? Okay, so somebody else tell me then what f sub y is. Thank you, Tally. Okay, everybody agree with that one? Excellent. So now that we've got first partials, what do we do? Set them equal to 0, right? All right, so the first one, 4x minus 2xy equals 0, is maybe not the height of friendliness. Neither of them really are. Why? Why are neither of those near as friendly as the things we were working with in the last equation? You have two variables. But you've got two variables, and you've got two equations, right? So it's solvable. Yeah, you could do substitution. That'd be a good thing to do. So if we wanted to do substitution, for example, we could... Hang on just a second. Yeah, so substitution would be a great option. I want to show you something, and you guys know how to do substitution, right? Where you solve for one variable and you plug it into the other equation. That would be a good option. This one will actually work a little bit cleaner than that, and the reason it will is because this first equation will actually factor so that the two variables are separated. So we're going to use that fact to our advantage so that we can avoid the drawn-outness, if you will, of doing a complicated substitution. So if we take a look at this first one, we can actually factor 4x minus 2xy. How? Take 2x out, right. So that leaves me with 2 minus y equals 0. So we actually have two things that we just solved for in this problem, right? One option is Y equals 2, and the second option is that x equals 0. One of these things has to be true, but they do not both have to be true. Okay? So if x is equal to 0, the first partial of x with respect to x will be equal to 0. So we have to come over here. We can then come over here to this and say if x is equal to 0, and we can evaluate this function when x is 0 and figure out what the y value is in that function to make that happen. So if x is equal to 0 over here, then I have 3y squared minus 3 equals 0. Right? All right, basic algebra question. What does this boil down to? What is y?
1. Positive.
There you go, plus or minus 1. So this just gave me 2 critical points. Now I have a critical point at 0, 1, and I have a critical point at 0, negative 1. But that's not the only possibility. X doesn't have to be 0. It's x is 0 or y is 2. So if y equals to 2, we can do the same kind of thing. We can evaluate this at 2. So I would have 2 squared, which would be 4 times 3 is 12. And then 12 minus my 3 is 9. So I have negative x squared plus 9 equals 0. So what would x have to be? Positive or negative 3. And this then gives me 2 other points that I need to test as well, right? I've got 3, 2, and negative 3, 2. So I have 4 critical points in this problem to test, and they aren't quite as straightforward as the last one in the sense that I can just sort of plug in and say, well, the other one's going to happen the same way. So we have to be a little bit more careful with them. All right, we've got our critical points. Now what? Second partials, you got it. So I need f sub x, x. Okay, I'm going to run out of space on this slide anyway. Let me just go to the next slide. All right, so we know f sub x we had as 4x minus 2xy. And f sub y is 3y squared minus x squared minus 3. So f sub xx. What is f sub xx? 4 minus 2y. Nice. How about f sub y, y? 6y. Is that it? Okay, good. And then f sub xy. Either x with respect to y or y with respect to x. Negative 2x is correct. All good so far? Now what? Yeah, we're going to do the determinant. So the determinant takes f sub xx, f sub yy, minus f sub xy squared. You don't have to write that every time, but I just want you to know what it is so that you're remembering, since we're still new at it. All right, so f sub xx, that's the 4 minus 2y. F sub yy is 6y. And f sub xy squared is negative 2x squared. In theory, we don't have to clean that up because we're just going to be plugging in numbers to it, but in practice, it's often helpful for the plugging in purposes to actually do a little bit of cleanup, especially with signs. So if I clean this up, what do I get? Looks good to me. Everybody agree? All right, now we have to evaluate the 4 critical points into this function. So we're going to do d of 0, 1. We're going to do d of 1, 0. I'm sorry, 0, negative 1. Then we're going to do d of 3, 2. And then d of negative 3, 2. So we're using this function and we're evaluating at these particular points. The first 2 are very nice because x is 0, so we only have the evaluation of event number 1. So go through. I'm going to pause. You guys get values. You don't need necessarily the value itself. You just need to know is it positive or negative. But go ahead and get the values so that we all can make sure that we have the right things. And I think, you know what, actually, let's pause right here. I want to show you a cool trick for your calculator. All right, grab your calculator out. TI 84s, 89 is going to work similar if that's what you have. But don't ask me exactly how to work it because I don't have one. And I'll keep my recording going of my voice so you guys can go back if you need to and to listen to these directions. Okay, so your calculators have the ability, this is not a terribly complex, I mean, you can put these numbers in, I have no doubt, okay? But sometimes they're messy and they're complicated and it's really easy to be off by a sign, and if you're off by a sign, that can make all the difference in the world in the end. So sometimes it's really nice because you can't actually, you don't have a three-dimensional way in your calculator to plug in numbers like an equation, right? Like we can do that if we just are trying to plug in x into a function, you know, that's just in terms of x. But how do we do it otherwise? Well, there's actually a feature in your calculator that allows you to store values. There's a button near the bottom on the left-hand side that says STO with an arrow. Does everybody have a button like that? Do you see that? Okay, so here's what we want to do. We want to store the values in here. So we're going to do this. You're going to hit that STO key. Actually, I'm going to take that back. First, you need to put the number. So we're going to store 0 as x, and we're going to store 1 as y, just the very first ones. So you hit the 0, you hit the store button, and you hit the variable x button. And then you hit the 1, you hit the store button, and the way you get the y is you've got an alpha button that lets you select all your buttons to turn them into letters. If you've ever typed anything in sort of actual typewritten words in your calculator, you know where that is. If not, ask me, because I want you to find where the x and the y, or where the y in particular is.
You just hit enter.
You just hit enter after each of them, and it just puts the number down there like you haven't done anything. It doesn't look like you did anything. Okay, so everybody good with that so far? So you've stored x as 0 and y as 1. Now, just so that you can see that it works, just type x and hit enter in your calculator. This doesn't mess up the graph by any chance, just so you know. But every time you hit x now, it thinks x is 0. And every time you hit y, it's going to think that y is 1. So what that means is you can put this equation into that regular screen in your calculator, 24y minus 12y squared minus 4x squared, and it automatically plugs in all the numbers for you. And it gets better. So do that one for me first and see what you get. So the joy keeps happening. Yes? You do the alpha button. Where is it? This one right here. So you hit alpha. Well, you hit store first. And you hit alpha. And then you see there it's y right, your x, y. So you hit that one. So alpha allows you to use all the green keys on your keyboard instead. And then it's store. James, did I hear you say you got a value?
12.
12? Did anybody else get 12?
Yes.
Excellent. I know Nidra's still entering hers, but everybody else has 12. Okay, so here's the cool thing, though. We're going to do the second one. We don't need to restore x. X is still 0, right? But now -1 is what y is. So you're going to do -1. You're going to hit the store button, and then you're going to hit y. And then you really don't want to enter 24y minus 12y squared minus 4x squared again, do you? No. So do you know how to not enter it again?
Go up and hit.
Yeah, so I don't know exactly how all of the calculators work because I know we've got some Inspires here too. But if you hit second enter, it brings up the previous line of text that you have just written. And if you do second enter a second time, it goes 2 lines up. And if you keep going, it keeps going up the chain of command for a limited amount of time. It is the coolest thing. It is so cool. So you second enter a couple of times till it brings up that equation you typed in,
I just go up.
and then hit enter.
Yeah, I need to do one.
That's because yours has a different type on. It doesn't work on all the calculators. Yeah, yours is special. All right. So did we get a value for that one yet?
Negative 36.
What was it?
Negative 36.
Negative 36. For 0 and x and -1 and y?
Yep.
Okay. Can we do it again? Sure. Now we're going to go in there and we're going to store that the x value is 3 and the y value is 2. So you do 3 store as x, 2 store as y. And then you can do second enter. 3 times probably is what you'll need to do at that point to get up 3 lines or 2 lines, whatever it needs to go up to pull back up that equation again, that expression again. And you're going to hit enter.
I think I trust my head, though, to be honest.
So
Yeah, my head got all. I got -12 and +36.
I got 12 on both of the first two, by the way.
I got 12 on both the first two as well.
Okay.
And the third one, though.
Third one, I got negative 36.
I get negative 36 down here. 12 is what I have written down up here.
Okay, those seem to go better. But I got
negative 36 for the second.
I've
Did
only
ya?
gotten 12 on all
Yeah, 4
of them.
times negative 1 is negative 24. Minus 12.
I may have typos written here too, so let's take a look here. Tally, what did you get when you plugged in the second one? Did you get you got negative 36? So Taylor, try that one again.
Is it?
Because I agree with Nathan, it should be negative 36, right?
Did you, when you did it under,
Because you have negative 24 minus 12, yeah.
yeah, it's just my calculator is wrong.
Okay, but did you find out what was wrong in the calculator to fix it?
I'm still trying to figure that out.
Okay.
But I know how to do it, so I was just, I mean,
Okay, how about this third one? What did we get?
Negative 36.
Is negative 36? And the last one?
Negative 36.
All negative 36 is at the end. All right, great. Okay, so if it's negative, that's actually a really good thing. Having a second or having a determinant value that's negative actually means that you know something, right? You know it's a saddle point. So these are all saddle points. What about the 12?
Find the f of x. You gotta do stuff.
You got to do stuff. That's exactly right. So once you know that this is 12, it's either a max or a min. You've got to look back at f sub xx. Okay, so f sub xx was up here. And that f sub xx has to be evaluated at the point 0, 1. So what will happen to f sub xx? We get a 2, which is positive. So a positive would actually mean it opens up.
Smiley face.
Smiley face, which means we have a minimum, right? All right, so it looks to me like we've got 0, 1 is the minimum. We've got 3, 2. I'm sorry, I missed one. 0, negative 1, 3, 2, and negative 3, 2 that are all saddle points. We all learned a really cool feature of your calculator, right? Woo. Okay, all of these things find for us. I'm sorry, yes, Brandon.
We just plug 0, 1 into xx.
It right here, you mean? Is that what we did? Yes, we did. We plugged in 0 in, which it doesn't have any x in it, but it's got a 1 in there, so we have 4 minus 2 times 1.
Okay.
Yes, that's correct. So, and if you're wanting to be a little bit more careful about it, you can use the notation where you put the point next to the function to indicate f sub xx at 0, 1, if that's helpful. Kind of like I did the d of 0, 1 at the beginning of that line. All of this finds local extrema, right? Do you have a question, Nathan? Local extrema. What is local extrema? What does it mean?
It's compared to stuff around it. It's
Compared to the stuff around it. It's all a comparison, right? So I always like to use the example that when we moved to Ohio, my husband was a youth pastor, and we had, most of our youth were, 10th grade, 9th grade kind of age at the time. And when we moved there, I told my mother how short I was, which I tend to think that I'm a fairly short person. I'm 5'4", and I may have shrunk since that point. I don't know, because you start shrinking as you get older, you know. So I'm 5'4". I don't consider that to be exceptionally tall, but my mother has different ideas. So every child but one in the youth group was taller than me. And these are all teenagers, right? So I'm looking around, I'm like, oh my goodness, look how short I am. But the reason that my mother doesn't think that is because in my family, I am the tallest girl in my family. So there you go, right? It's the local area that you're talking about, right? It's the constraint upon which you're sort of thinking, you know. And so that's what's going on here. We're getting local extreme values. So we're going to do a couple of things. One is in this section, and the next is going to be in section 8, where we're going to be working with absolute extrema, but in a different context. So here's our first one. So let's talk about this one. I'll give you the directions and I'll show you how this works a little bit differently. So we're going to find the absolute extrema of the function on the region that is given. So here's my function, x squared plus 3y plus 3x squared, or 3xy, excuse me. And we're going to take a region that's bounded by three equations. Y equal x, y equals 0, and x equal 2. So the first thing I'm going to actually do is I'm actually going to draw that image that I'm getting, sort of verbal description anyway, those equations. We're going to look at a graphical image. So we know what the line y equal x looks like, right? It's the diagonal line like this, 45-degree angle. That's not a very good one. Let me try again. That's a little better. So there's my line y equal x. We've got the line y equals 0. Where's the line y equals 0? That's the x-axis, right? And then we've got the line x equals 2, so that's a vertical line over here at 2. So we're trying to figure out in this triangular area, where is the biggest value? Where is the smallest value? So this is something akin to being, in the middle of the mountain range and you're wanting to know where the highest point is in a specific area that you're allowed to, traverse the area or whatever. You can't walk everywhere. Somewhere it's too many trees, or there's a river running through it or something. You can't walk in all of it. So there's a limited scope of where you can actually talk about there being a maximum or minimum value. So that's what we're doing here. So the question is, how does that change what we're doing? Well, it just adds a layer on top of it is what it does. All right? So we have to test those local extreme points. So we're looking for, let me write down a few things here about what we must test. So we must test, number 1, all local extrema in the region. Okay, I don't care if there's, for the purposes of this description, I don't care if there's a maximum outside of this picture. That's not the point. I'm not allowed to go there. I'm supposed to be staying within the triangle, okay? So the second thing I need to test is I need to test along the boundaries that are given. So that's along each equation. So along the equation x equal y, along the equation x equal to 2, and along the equation y equal to 2. And the third thing I have to test is I have to test the vertices of the region. Okay, so in this case, what are my vertices? Let's just label those right now. I've got 3 of them. 2, 2, that's correct. And 0, 0. So you already know 3 points you're going to have to test in our argument. We need to figure out what happens at those 3 points. So testing number 3 is not a hard thing to test. Generally speaking, the equations you're going to be given for boundaries are things where you can solve them pretty easily and figure out what the x value and the y value are where these equations cross. Along the boundaries given is going to look a little bit different, and you already know what along the local extrema in the region, how to do the local extrema from what we've done before. So, taking a look, we're going to start with the local extrema. That's what we've been doing in this section and we're most familiar with. How do I find where I have local extreme values? So my equation originally, just so I have it over here, is fxy equals x squared plus 3y minus 3xy. Yes, first partials is where I need to go. So f sub x is what?
2x minus 3.
Good, 2x minus 3y. Someone else, what is f sub y? 3 minus 3x. Okay, so those are my two partials. And then what do? I set them to 0. Which one's the easier one to work with? F sub y, right? 3 minus 3x. So if I solve this one, what does x equal? 1. X must be 1. That's my only choice for this one, so I get exactly one possibility. What's even better is that when I take that x equal 1 and plug it back into the other equation, I only get one possibility there as well. What does y need to be? 2/3. And we do need to pause for a moment and think about the fact that this value, 1 and then 2/3, is it actually inside the triangle or not? Because if it's not, we don't want to use it, no matter the fact that it's a possible extrema or not. So let's look back over here and figure it out. Is it inside of this area? Yes, it definitely is. So I can go over here to x equal 1, and if I went all the way up to x or y equal 1, it would be before that. So it's going to be in that purple shaded area. So this is one of my test points as well. Now, I do not need to test whether it's a local extrema. That's not the question. So I don't need to go through and actually do that second derivative test. So refrain from trying to do that, okay? It's not necessary. But I need to test one more thing. What was the second one? I've bounced around. I did number 3 first, and then I did number 1. Yeah, so this is number 1. This, finding these points over here, was number 3. We'll test them and everything in a minute. And number 2 is the boundaries. So what does that mean? Well, we're going to take each boundary one at a time and think about along that boundary what kind of an equation we get out of our function. So one at a time, we'll start with along y equals 0, because that's kind of nice. So along the equation y equals 0, if I take my function and I put in y as 0, what am I going to have? X squared. What do you know about minimums and maximums on the graph of x squared? There's one. It's a minimum, right? At x equal 0. So in fact, I think I wrote it down earlier as an ordered pair, so I'll do it here. At x equals 0. So this gives me the point 0, 0. I'm actually already testing 0, 0, so that doesn't give me anything new. But it is a possible place where I could get new information. Another equation. Let's go along the line x equals to 2. So I'm going to do 2, 0. I'm sorry, not 2, 0, 2 at y into my function. So if I take my function and I plug in 2 for x, what do I get? 4 minus 3y is correct. What is that an equation of? A line. What do you know about lines?
They don't have their extremes.
There's no extreme value on there, right? There's no possible local extrema. So this one has no local extrema. So the last one is along the line y equal x. So you can either plug in all the x's as y's or plug in all the y's as x's. It doesn't really matter. I think when I wrote it down, I put in all the y's as x's, so it looks like fxx. So I've got x squared plus 3x minus 3x squared, which gives me what? Okay. And this is a parabola. We could actually talk about the vertex and use the vertex to talk about the minimum. Or we can use a little calculus and we can do the derivative. This is just a function in terms of x at this point. So we could take the derivative of this and set it equal to 0, which is easier than finding the vertex. So that's what I'm going to go with. If we take the derivative of this, what do we get? Negative 4x plus 3. And we set it equal to 0. Then what does x equal? 3/4. And this is actually, if I remember right, this is one, this may be an odd one of your book, and I was looking, checking my solutions afterwards with the back of the book, because it's a good idea to do that, and they actually have it wrong in the back of the book. They actually wrote this as 4/3, or I think this is the one. There was one recently where they did that. So just do be wary of that. Sometimes the back of the book's not right. All right, so this is the maximum. So if x is 3/4, y is also 3/4. Why? Yeah, because y equals x along this curve. So I've got these 2 points, but the 0, 0 I already had. I've got this point right here, 1 2/3. And then back on the other side, I have the additional 2, 0, and 2, 2. So I actually have, and I've got the 0, 0, but I already counted that one. So I've actually got 5 points to test. Agreed? Okay. So do you remember when we worked in Calc 1, when you worked in Calc 1, whenever you did it, what you did next once you had these sort of possible places where you might have extreme values for absolute extrema? Do you remember what you did? You plug them back into the function, and you decide which one's the biggest and which one's the smallest. So we're going to take our function with all of these values. So I had 0, 0. I had 2, 0. I have 2, 2. We had 1 2/3. We have, what was the other one? 3/4, 3/4. So you can do these in by hand, or you can do these with the store feature that I was showing before into your function. X squared plus 3y minus 3xy. And we actually need to know values here. We do not just need to know signs. We need to know the actual numerical value that we get in fraction form, decimal form. It doesn't necessarily matter, but we do need to know the actual numerical value that we get for these. So everybody give them a shot and see what you get for all 5 of these.
Where did we get the 1 2/3?
We got it from the from actually finding the local on the entire surface, the local possible the local critical point. We found a critical point for our surface. Yep. Yeah, so the equivalent to what we did when we did Calc 1 is you had to find local extrema, and then you had to test endpoints. Right? That's what you had to do. You had to find whatever possible local extrema you had in the interval, and then you had to test the 2 endpoints of the interval. Here, we just have so much more boundary that we have to test. So we have, the local in the interval, which is our shape, the surface in the case triangle, and then we have along the boundaries, and we have those corners of our boundaries as well. Does anyone have the f of 0, 0 yet? Okay, that one's 0. Good. What about 2, 0? 4. Anyone have 2, 2? Negative 2. Those ones are quick and easy to just do it without even thinking too much. The others are a little more complicated because of the fractions that are involved and some squaring and things like that going on. So what is f of 1 2/3? 1. Okay. And how about f of 3/4 3/4? 9/8 is correct. That look good to everyone? I mean, it can look messy and still look good. Does it look good to everybody? Okay. All right, so the question is, which one's the biggest, which one's the smallest? So let's go with that. Which one's the biggest?
4.
And the smallest? Yes. So this is max, this is a min. What's even better is you actually found the ordered triple in doing that, didn't you? Because this is actually a 3-dimensional shape, correct? So you could actually talk about the max being at 2, 0, 4. You can talk about it being at 2, 0 as well, but just be aware that the 4 is actually the height, if you will, at that point. And the minimum then is at 2, 2, negative 2. All right, any questions on that? All right, let me give you the homework for this section before we take a look a little bit into the next one. This is page 884, numbers 1, 3, 4, 7, and 8, 10, 32, and 34. Does everybody have it written down? You're good?